Measures of spread are descriptive statistics or summary statistics, and they fall under the data analysis step in the statistical investigation process. Generally, the first descriptive or summary statistic looked at is a measure of centre, but alone this can be misleading. A useful numerical description of a distribution requires both a measure of centre and a measure of spread. The problem with using just the range and interquartile range as a measure of spread is that both only use two data values in their calculation. The preferred measure of spread is the standard deviation. In this video, we're going to look at a reminder of what two measures of spread are, the range and interquartile range. We'll also look at in detail what the standard deviation is, and we'll look at calculating the standard deviation with some examples. We'll also look at the properties of the standard deviation and choosing which measure of centre and spread together. For a single data set, we've already discussed two measures of spread. The first one we looked at was the range, which is the difference between the largest or maximum value and the smallest or minimum value. The second was the interquartile range, which is the difference between the upper quartile and the lower quartile. The problem with using these as a measure of spread is that both only use two data values in their calculation. Please watch my video on measures of spread if you need further information on how to calculate these. Another statistic commonly used to describe the measure of spread is the standard deviation. It's a number that describes how far data values are from the mean. A data set with a relatively small standard deviation will have values concentrated about the mean, and a data set that has a relatively large standard deviation will have data values more spread out from the mean. In many common situations, we can expect 95% of data to be within two standard deviations of the mean. This will make more sense when we look at the normal distribution. Let's look at the sample standard deviation first. If we have n values in a data set, and they are x1, x2, xn, the sample standard deviation is usually denoted by S and is written as follows. First, we minus the mean from each data value, then we square them and add them together. If we simply took the average of the deviations, we'd get 0, so we square them, which makes them all positive. Then we divide the number by the number of values, minus 1. Finally, because we squared the original deviation, we take the square root of the whole thing to convert back to the original units. Similar to the mean formula, this formula is usually written in a slightly different manner using the Greek symbol or Greek letter sigma, which looks like an M on its side. This means sum of. You may notice that I've been referring to the sample standard deviation. In statistics, samples and populations have very different meanings, and these differences are very important, even if they're calculated in a very similar way. To acknowledge that we are calculating the population standard deviation and not the sample standard deviation, we use the Greek lowercase letter sigma. In reality, it's difficult to obtain data from all members in the population, so the exact value of the population standard deviation is not known. Instead, we collect a sample and use the standard deviation of the sample to approximate the standard deviation of the population. We write the standard deviation of the population and of the sample respectively as follows. More on these in a moment. The sample standard deviation is for a sample data set drawn from the population. If every data value from a population is used, then we calculate the population standard deviation. I'll summarize the notation here of both the mean and standard deviation for you. If the data represents the complete population, then divide by n instead of n take 1. This can be seen in the formula. This would give the population standard deviation. Divide by n take 1 for the sample standard deviation. This gives a better estimate of the population standard deviation. The process is like finding the average of the difference between the value, or the data value, and the mean. The difference called the deviation is squared because its average would be 0 if we didn't. We then square root the entire thing to turn it back into the same units. Remember, squaring and square rooting are inverse operations. The process for finding the standard deviation is find the mean, find the difference between each value and the mean, called the deviation, square each deviation, sum the deviations, divide by the number of data values less 1 or minus 1, take the square root. Again, the formula looks like this. Let's work through the process with an example. town planner is investigating the height of buildings in the city. To inform their analysis, they plan to calculate the standard deviation. They measure a height of a sample of buildings in the city. The heights of the sample are written here in red. The first step is to find the sample mean, or x bar, which is 31 meters. I've marked the sample mean here on the chart so that you can see where it lies relative to the height of the buildings. The next step is to find the difference between the height of each building and the mean. This is the part in the brackets in the formula here. Like I said earlier, if we simply take the average of the deviations, we'll get 0. Instead, we square each deviation, sum the square of each deviation, divide the number by the number of observations minus 1, then take the square root of that number to turn it back into the same units. Here I've simplified the formula. You'll notice that the number in yellow matches the deviation on the chart, so that's the difference between the height of the buildings and the average height of the buildings, or mean height. Simplifies further. Then we solve for S, which stands for the sample standard deviation, which is 18.5 meters. Remember, the mean is approximately 31 meters. Here I've marked one standard deviation from the mean, so that's the mean plus or minus one standard deviation. You'll notice that 5 out of the 6 buildings here are within one standard deviation of the mean. If I mark 2 standard deviations from the mean, so I've done the mean plus 2 standard deviations above, 100% of the buildings fall within this. Remember before I said that we expect 95% of the data to be within 2 standard deviations of the mean. In this case, 100% of the data values are within 2 standard deviations of the mean. Let's look at another example. First, we find the population mean. For each data value, we can then calculate the deviation from the mean. I've put this in a table here. If we took the average of the deviations, we'd get 0. Instead, we square them to make them into all positive values, and we find their average. Finally, since we square the deviation, we have to square root it back, and then we can simplify it, and we get the standard deviation of this population. So remember, population, we didn't divide by n take 1, we divided by n, which was 7. And the population standard deviation is approximately 13.3. Here we have a sample data set given in a stem and leaf plot. We still know all the values, therefore we can calculate the standard deviation. This time it's a sample, so we find the sample mean, it's x bar is 18. And now we can find the standard deviation, which is S in this case because we're looking at a sample. And we can work out our deviations, square them, add them all together, divide by n, take 1. The number of values is 16, so we take 1 and then square root the whole thing. And we can simplify that to S, or the standard deviation, is approximately square root of 66.7, which is 8.17. Consider this back-to-back stem and leaf plot. At night attendance, we've got the mean of 33 students and the standard deviation of 7. For the day attendance, we've got a mean of 20 students and a standard deviation of 5. By looking at the stem and leaf plot, suggest why the day attendance mean is less than that of the night attendance. So here we just got to interpret the data. Almost all the day attendance numbers fall between 10 and 30, with one exception. Majority of the night attendance numbers are greater than 30, which is why. Why is the night attendance standard deviation larger than that of the day attendance? The data for the night attendance is more spread out than the day attendance. The day attendance is closely clustered near its mean, which is the answer to that. Finally, let's give a practical reason why there's a difference between the center and spread for the data for the day and night classes. So I think people attending the night classes usually do so because they work during the day. This might suggest they have other commitments that impact their ability to attend. Therefore, attendance has a higher spread than the day class, but night attendance has a higher spread than the day class. The mean might be higher because there's less classes at night than the day, therefore less choice and higher attendance at the night classes, and leading to a higher mean. Let's quickly look at some of the properties of the standard deviation. So it measures the spread around the mean. Because of its close link with the mean, standard deviation can be greatly affected if the mean gives a poor measure of central tendency. Remember from my video on measures of centre and which measure of centre is most appropriate, the mean is affected by outliers. The standard deviation is also influenced by outliers. One value could contribute largely to the result of the standard deviation. Like the mean, the standard deviation has the same units of measurement as the original data, whether that is meters or millimeters or whatever the measurement is. When all the observations have the same value and there's no spread, the standard deviation is 0. Otherwise, the standard deviation is greater than 0. This makes sense because the mean of a set of values that are all the same is also the same value. If we take this away from the values, we get 0. So we'd have 0 deviation. We now have a choice between two measures of centre and measures of spread, the median and the interquartile range, and the mean and the standard deviation. The median and interquartile range are usually better than the mean and standard deviation for describing a skewed distribution or a distribution with outliers. You use the mean and standard deviation only for reasonably symmetric distributions that don't have any outliers. Please note that it's very important to plot your data because the summary or descriptive statistics do not fully describe the shape of a distribution. So in summary, in this video, we've had a look at what the measures of spread are again, the range, interquartile range. We had a look at standard deviation, calculating the standard deviation, the properties of the standard deviation, and then choosing between the measures of centre and measures of spread. Thank you.